This is the last section we're going to cover in this course, and it's also the culmination of our studies of growth. So we've looked at pushing the limits of growth and size, and in this section we're going to focus on how humans grow from birth to adulthood. Obviously, an adult is not just a linearly scaled up version of an infant. If you saw an adult who had the same proportions as an infant, they would probably look pretty strange. As a general rule, most creatures can grow according to geometric similarity up to a factor of about 2. And from birth to adulthood, a person's height goes up by a factor of around 3 to 3.5. So we're not going to grow in a geometrically similar manner. There's going to be some changes in proportions there. Also, when we looked at scaling up King Kong from an average gorilla, we saw that we would need a scaling factor of about 9. So there would probably need to be some pretty significant changes in physiology to get an ape that is actually 50 feet tall. Let's take a look at how people change as they grow. This graphic here in the corner shows how proportions change as we grow from a baby into an adult. You can see that a baby's head is about 1/3 of its total length, while an adult's head is about 1/7 of their height, so it's much smaller in proportion to their body. A baby's arms are also about 1/3 of its length, but an adult's arms are about 2/5 of their height, so adults' arms are slightly longer in proportion to their height. So we can see that the body as a whole does not scale geometrically, but if we look at different parts of the body, some of them do scale geometrically with different linear scaling factors. A baby's arm is going to have the same structure as an adult's arm. It's just going to be smaller in size, so that grows pretty much geometrically. Some parts of the body change in shape as well as in size as we grow, and one part where we can see this change in size and shape is a person's head. And we can model the process of a baby's head growing into an adult head using graph paper. So you can see here a baby skull drawn on a grid, and then that grid has been deformed and stretched out until it takes the shape of an adult skull. So that would be one way to model the growth of a skull. And a method similar to that one is used to help find missing children. That method of deforming features according to observed growth patterns is how age progression photos of missing children are produced. So even if the child went missing as a very young baby, we can get a very good idea of their appearance years later. So this was a story that was in the news a while ago. This young woman was taken when she was just an infant and found when she was a young adult that the person who she thought was her mother was not actually her mother. And here we can see the actual photo of her as a baby, the age progression to age 19, and then her actual photo at age 23. So it's a pretty good likeness, not exactly the same, but enough to give you a good idea of the features of this person. The important mathematical concept for this section is allometric growth. Allometric growth is growth of the length of one feature at a rate that's proportional to a power of the length of another. So we saw some allometric growth actually earlier. We saw that area grows like the square of length. So we had A was proportional to L squared. And also that volume grows like the cube of length. So V is proportional to L cubed. And we're going to see some other relations in this section with different powers here instead of 2 or 3. For example, we can look at arm length and see that this grows at a rate proportional to a power of body height. So we saw that arms get longer relative to height as a person grows. This graph shows how arm length grows with body height, and we can see that the pattern doesn't exactly follow a straight line. You've got kind of a curve here in between the first two data points, and that curve indicates that that's an allometric growth instead of geometric growth. So up to 0.75 here, or 9 months, we see allometric growth, but it's hard to tell what power of body height arm length grows in proportion to from this graph. So to figure that out, we need to first talk about the logarithmic scale. In the graph on the last slide, the tick marks on the axes were evenly spaced and marked off even intervals of 20 centimeters. And this is called a linear scale, and it's what you're probably used to. Linear growth on this type of graph is going to look like a straight line. So if I go back here, you can see that further on this does look like a straight line, so maybe after about here this looks like linear growth because it's a straight line, but up to there it's not quite a straight line. Another useful type of graph that we're going to look at in this section has a logarithmic scale, which uses intervals corresponding to orders of magnitude. And what that means is that the axes are going to be marked off with powers of 10 in our case. So we'll have a tick mark at 1, which is equal to 10 to the 0, a tick mark at 10, which is 10 to the 1, 100, which is 10 squared, 1000, which is 10 cubed, and you can keep on going. But these will be evenly spaced out, so it'll look like this. So I could start at 1, and then a little ways over I'd be at 10, and then I'd go over the same amount, and now I'd be all the way at 100, and then at 1000. So that's what that's going to look like. So let's go back here. This graph shows the same data points that we saw earlier using logarithmic scales. So you'll notice on the bottom that the horizontal axis starts at 10 here. Then in the middle is at 100, and the end over here is at 1000. And the vertical axis is similar, but it just goes from 10 to 100. And we've got all these additional tick marks in between just to make it easier to read. So now our graph doesn't look curved anymore. It looks more like a bent straight line. So we can divide this into two straight line segments here. The first segment going up to 0.75 or 9 months has a slope of 1.2, and then after that the line's got a slope of 1.0. Since the slope is greater than 1, this means that the arm length is increasing relatively faster than height, which is what we should expect since the arm gets longer in relation to height as you get older. In fact, if A is the arm length and B is body height, then they have this relation here. A is proportional to B to the power of 1.2, which is allometric growth. So the important thing here is that the slope of the line in my logarithmic graph here is equal to the power of the relationship for allometric growth. So that's the important thing you should know here. Keep that in mind. Now if I look at the second segment after 9 months, that has a slope of 1.0, so that tells me that A is going to be proportional to B to the power of 1.0 after 9 months, and that's just the same as B. So I've got A is proportional to B, which means that arm length is going to grow pretty much geometrically with body height once you're over 9 months old. Let's finish up the section by looking at an example. The chart below shows the number of species of reptiles and amphibians on some Caribbean islands, together with the approximate areas of the islands. So here I've got Redonda is the smallest island with an area of 1 square mile and 3 species of reptiles and amphibian. And Cuba is the largest island with an area of 40,000 square miles and 76 species of reptile and amphibian. And here I've got a couple of graphs of the data from that chart. The first graph shows the data with linear scale axes, and the second graph shows the data with logarithmic scale axes. And there's also a power regression line fit to the data on the second graph. So I'm looking at these graphs and I want to answer 3 questions. First, does this relationship show geometric or allometric growth? Second, looking at the equation, how is number of species proportionally related to area of the island? And third, how many species would you expect to see on an island with an area of 10,000 square miles? So I'm going to give myself some more room here. So first, let's look at the relationship and decide if it's geometric or allometric growth. Well, this certainly doesn't look like a straight line, so that's not going to be geometric growth. It looks more like a curve. Maybe I could draw it as kind of this type of curve here. It looks like I've got an outlier, and this will be the point for Trinidad, which was 2,000 square miles but had 80 species, so that's going to be an outlier. But if I look at my logarithmic scale graph here, then I can see that that fits actually pretty well to this straight line. Again, I've got my outlier here, so that's off a little bit, but maybe I don't want to pay too much attention to that. So it looks like this relationship is allometric growth. So looking at the equation, how is the number of species proportionally related to area of the island? I've got an equation for this line here. I'm going to rewrite it so you can see it better. It's kind of small there. F of x, which is the number of species, is equal to 3.11 times x, if x is the number of, or the area of the island, to the power 0.32. So I said that the power is the same as the slope of the line in a logarithmic graph, and this tells me, so f of x is the number of species, then that's related to the area of the island to this power 0.32. And lastly, I want to find how many species would I expect to see on an island with an area of 10,000 square miles. So to find that, I would just need to plug 10,000 into my equation here. So I get f of 10,000 is equal to 3.11 times 10,000 to the power 0.32. So I'm going to put that into my calculator, and I'm going to round to the nearest whole number. Since we have to have a whole number of species, we can't have a decimal number of species, and that's going to give me 59. So I'd expect to see 59 species on an island with an area of 10,000 square miles. So that's the end of this section. Here are the things that you should know. You should be able to know that growth patterns are often more complicated than geometric similarity, and also understand what allometric growth is and be able to identify it if given a graph showing data with logarithmic scale axes. So basically, if you're given a problem that's similar to the example we just did, you should be able to do all the parts of that problem.